In this figure, we're going to look at pacemaker enzymes and their role in regulating the rate of metabolic flux along particular metabolic pathways. And a metabolic pathway is simply a sequential series of enzymatic reactions, such as glycolysis or the Krebs cycle. And so in those pathways, we have incoming substrate that gets processed by a number of sequential enzymes, enzyme 2, enzyme 3, all the way down to enzyme 6 here in this particular pathway. And then the output would be the product of that metabolic flux or that metabolic pathway. And so how do we regulate the rate or the output of this particular pathway? Each enzyme does not have equal control over that overall output. As you can see in our sort of hypothetical pipe model here of a metabolic pathway, enzyme 3 is very wide open. And so flow through this particular pathway or section of the pathway is unimpeded, right? So this is not a regulatory site. Constricting this down, slowing down enzyme 3 somehow would not really affect the overall flux of this pathway. However, if we look at enzyme 4, this is a bottleneck enzyme. It's the rate limiting step overall. And so this is where we want to put in our regulatory factors to either speed up or slow down the metabolic flux along the entire pathway. Now that can be either activating feedback going to the right or inhibiting feedback going to the left. And our feedback often comes in the form of the product feeding back to modify the activity or the expression of this bottleneck enzyme. For instance, the concentration of ATP feeds back on the bottleneck enzyme within glycolysis to help regulate that output, right? If ATP is in abundance, then we don't need more ATP, and we can impede the activity of that enzyme. That would be a shift to the left here. Conversely, it could go the other way. ADP, if ADP is dominant and ATP is lacking, well, then we might want to activate this particular enzyme, reduce the resistance here, right? It gets opened up. And the way we open it up is we either increase the enzyme amount. If we increase the enzyme amount, we have more binding sites and our rate will go up. Or we can increase the efficiency of the enzyme. That would be measured by its rate constant, by either increasing its turnover rate, right? How efficiently and rapidly it processes the substrate, kcat, or by increasing its affinity, denoted by a decrease in km. And so if this rate constant goes up, we would reduce the resistance to passage through that particular enzyme, and our metabolic flux would go up. Conversely, if we have inhibiting feedback, right, we decrease the activity or expression of enzyme 4, our bottleneck gets tighter, right? We've constricted this, and so our metabolic flux in that case would go down.